In this video, we're going to cover stoichiometry and limiting reactant, which are really, this is all the same sort of an idea. It's a way of thinking through multi-step processes based on what we know from chemistry. So just like any stoichiometry problem, you have a balanced equation. You give your given units, grams, liters, numbers of particles, transfer them into moles. Moles are our common conversion in all of these situations. Set up a mole ratio, cross multiply, cancel out the units you don't want, keep the units that you do want, and then going from moles to requested units is the next step. Now again, it's very hard to just look at these rules in isolation. Limiting reactant, I've thought about the rules. I mean, they're very much, the first three are very much similar. The fourth one is where we have to do the calculation. I initially said step 3A, but it really probably belongs more in step 4, where you cross multiply, you cancel out the units for the different quantities, and then that's where you're going to find out which of the reactants will yield less product. That'll be your limiting reactant. Then you take your moles and requested units, working from the limiting reactant, working from the product that you can only produce with the limiting reactant. Once the limiting reactant runs out, you don't have any more product. And then if there's a situation we need to calculate excess, which we will see problems also, that might be an extra step to do. So really the steps aren't that much different from limiting reactant. It's basically a type of stoichiometry. The rules are very similar, and I don't know if it's necessarily helpful to just look at the rules as they are. It's really all about doing problems and getting through the problems. Now, this one I thought was particularly tough, not for the equation, not for the concept, but just because this was a tricky problem because we included some unit conversions. So the question first is, which reactant is limiting? Out of a 1 gram sample of magnesium is ignited as burned in a flask containing 5.00 times 10 to the 15th cubic micrometers of oxygen at STP. Again, accelerated students are expected to be able to transfer units, are expected to change units from one to another, really at all levels. So we'll get through this. We haven't seen this in a while, but really we haven't done any dimensional analysis in quite a while, and that's why we haven't seen this for quite some time. But the question is, which reactant is limiting? So we first need a balanced formula. This equation as it stands is not balanced because we have O2 and we have 1 oxygen here. O2 occurs in nature, so we have to balance it in a way that we get our O2 to behave as it should, plus 2 magnesiums in this case, and then we make magnesium oxide, and I just realized that is not correct. So now, back to where we were. That is a balanced equation. 2 oxygens, 2 magnesium, 2 magnesiums. Step 2 is to convert our grams to moles, and we do that with the gram molar mass of magnesium. We find out how many moles of magnesium we have. We have to do the same thing with oxygen, except we have cubic micrometers of oxygen. I'm not entirely sure how necessary it is to put you through this, but this is the problem as it is stated. It's the thing that made everybody grumpy at the beginning of the year. We're probably going to see it quite a few times again, including on the final. I wouldn't be surprised if we see some sort of unit conversions on the final. So let's get through this. We need to know micro is a millionth. So 1 meter is a million micrometers, or 1 micrometer is 1/1,000,000th of a meter, also called a micron. If you're working with biology, it is actually a very useful measurement because a lot of cells are at the micron level. We also know that a liter, which is, we're talking about a volume of gas. A liter is 1,000 milliliters, and it just so happens 1 milliliter is the same thing as 1 cubic centimeter. So it might not be immediately apparent that we could go from micrometers to milliliters, but if we know that milliliter is 1 cubic centimeter, now we have a better idea of what we might be able to do. especially because 1 liter would therefore be 100 cubic centimeters. But in order to figure that out, we need to go from a meter to centimeters. So 1 meter equals 100 centimeters, 10 to the 2 centimeters. If we check and we divided 10 to the 6 micrometers by 10 to the 2nd centimeters, we'd find out that 1 centimeter equals 10 to the 4th micrometers. Now we're in a state where we can actually figure out what we might be able to do. We have a conversion here. 1 centimeter equals 10 to the 4th micrometers. Therefore, we were given 5.00 times 10 to the 15th micrometers cubed, and we need to take that value with our conversion that we know. 1 centimeter is the same as 10,000 micrometers. We need to cube that in order to get our cubic micrometers at the bottom, what they're going to cancel out. And now with these exponents, you need to multiply them. So that would be 5 times 10 to the 15th micrometers cubed times 1 centimeter cubed over 10 to the 12th micrometers. That should be cubed. I need to get that onto the panel here. And let me get this tiny bit back. Okay, so now our units will cancel out as we would expect them to. So 5 times 10 to the 15th micrometers cubed, they're going to cancel out. My answer is going to be in centimeters cubed. When I'm dividing, which I really want to have something on the top, I have something on the bottom, I'm dividing, I'm subtracting my exponents, and we can eliminate the grumpy cat there. We can say that, and actually on this slide also I need to add the centimeters cubed just to make sure I'm consistent about everything. So here we go. 10 to the 12th micrometers, that will equal 5 times 10 to the 3rd cubic centimeters. So if we put this into standard notation instead of scientific notation, 5 times 10 to the 3rd is the same as 5,000. 5,000 cubic centimeters is the same thing as 5,000 milliliters, and 5,000 milliliters is the same as 5 liters. So after all of that effort, we were able to establish how many liters of oxygen gas we have, which is the main point of that whole mangled calculation there. But now we know we have 5 liters of oxygen and we have 1 gram of magnesium, and we need to figure out what our limiting reactant is. So we need to go to our calculations we had previously. The magnesium problem has already been solved, but we have the 5 liters of oxygen. We need to convert that into moles, because again, every equation is based on a mole ratio. This one's not balanced, this one is. So it would be 2 moles to 1 mole to 2 moles, which again, I need to correct. These are different slides, which means I haven't gone through every single one to correct them yet. So 2 moles of magnesium would give me 2 moles of magnesium oxide if I combine it with 1 mole of oxygen gas. That is all moles. It's not grams, it's not liters, it's not number of, well, it potentially could be number of particles wherein 2 atoms of magnesium and 1 molecule of oxygen would give you 2 formula units of magnesium oxide. But better to understand these as molar values. So we're converting 5 liters of oxygen at STP, which it states there, into moles. We do that by multiplying by 1 mole over 22.4 liters. I cancel out my liters. I get 0.223 moles of oxygen gas. My mole ratio is 2 to 1 to 2, as I can see right here in my balanced equation. Now I need to calculate how much product will I make with all of my magnesium being used up, which I got from here above, or will will I get more product from my magnesium being used up, or will I get more product from my oxygen being used up? Now, 1 gram is not a very large amount. 5 liters is 2.5 of the big soda bottles. So that's a pretty decent amount of oxygen. And I didn't animate this arrow. It kind of gives away where our answer is. But it is basically a 2 magnesium oxide to 2 magnesium ratio, which is the same thing as a 1-to-1 ratio. So if I'm putting in 0.0412 moles of magnesium, I'm going to get out 0.0412 moles of magnesium oxide because the ratio is 2-to-2, or reduced, that would be a 1-to-1 ratio. With oxygen, it's a 1-to-2 ratio. So for every mole of oxygen gas, I make 2 moles of magnesium oxide. I already know that I have 0.223 moles of oxygen. Basically, I'm going to cancel out my moles. I didn't do the cross multiplication, primarily because I didn't have the room to fit it on the slide. But this system works just as well as the cross multiplying, as long as you know what you're doing. You have your mole ratio right here. This is an equally valid way of calculating your moles of magnesium oxide that would be produced from 0.223 moles of oxygen gas. So with that, we've established that magnesium is going to run out before the oxygen runs out, and therefore the equation is going to stop when I make 0.0412 moles of magnesium oxide, because at that point I will not have any more magnesium to continue the reaction. So the next part of that question, we already established. Part A was asking which reactant is limiting. We've established that now. Now we have part B, keeping my equation up here as a reference. Part B is the amount of excess reactant in grams. So again, we sort of have gotten part of this already. We knew how many moles of oxygen we had. We established that 5 liters of oxygen gas is 0.223 moles of oxygen gas. If all of my magnesium oxide is produced, we can use that as our reference to figure out how much oxygen was used in order to make that. And again, for every 1 molecule of oxygen, or every 1 mole of oxygen gas, 2 moles of magnesium oxide were produced. So we're going backwards, and to find out in reverse how many moles of oxygen gas were used for this reaction, it turns out that it is basically your 0.412 moles divided by 2, because it was a 2-to-1 ratio of magnesium oxide to oxygen. So I got 0.0206 moles of oxygen used in the reaction. I started with 0.223 moles of oxygen. I used 0.0206 moles of oxygen. That means I have 0.202 moles of oxygen remaining, sitting around in the container, not able to conduct any reactions because the magnesium has already been used up. Once I find out how much of my oxygen's been left over, I just go from moles back to grams, keeping in mind this is oxygen gas, O2, therefore the gram molar mass is 32 grams and not 16 grams because it is O2. That's why we always must keep track of our subscripts and our coefficients, 2 very important things to remember. So we get 6.46 grams of our oxygen left over. And then it asks how much of our product would we get in grams, the product being magnesium oxide. We've already established that we make 0.412 moles of magnesium oxide. The gram molar mass would be 24.3 plus 16, which is 40.3. I cancel out my moles. I end up with grams on the top, and I get 1.66 grams of magnesium oxide produced in this reaction. Limiting reactant can also be combined with percent yield, which is what happens in the remainder of this video. The problems, I think, here, these are excellent problems. The equations are actually very, very simple. Here we have calcium combining with chlorine gas and making calcium chloride. There's no other product you could possibly make with calcium and chlorine, calcium chloride. Very nice thing is that is a balanced equation. 1 mole of calcium and 1 mole of chlorine gas is going to make 1 mole of calcium chloride. The reason being that calcium will give away 2 electrons to the chlorine molecule. The chlorine molecule will turn into 2 chloride ions. So you have calcium with a +2 charge and 2 chloride ions with a minus charge. And it is a solid, it's a salt. It's actually used in ice melt lots of times because it's a little less damaging to the environment than sodium chloride. What we know is we have 25.7 grams of calcium. And so the first thing we want to do is figure out how many moles that is, because when we plug that into our mole ratio, we can figure out which of our reactants is limiting. 25.7 grams of calcium times 1 mole over the gram molar mass of calcium gives me 0.641 moles of calcium. I do the same thing with chlorine gas, except I have to remember I'm given liters for chlorine gas. I'm not given gram molar mass. We've got to be very careful. You can't do 71 grams because you're given liters for chlorine gas at STP. So 10 liters of chlorine gas times 1 mole over 22.4 liters is going to give me 0.446 moles of chlorine. Now I could continue my calculations and figure out how much product I would make if all of my calcium was used up and all of my chlorine was used up. But seeing as this is a 1-to-1-to-1 ratio, if I used up all of my calcium, I would make 0.641 moles of calcium chloride. If all of my chlorine were used up, I would make 0.446 moles of calcium chloride. Therefore, chlorine is my limiting reactant. And as a result, 0.446 moles of chlorine gas will yield 0.446 moles of calcium chloride. The next step would be to find my mole ratio. I see my animations are... The challenge is, just for the record, when I put so many of these in my PowerPoint, it's very hard to see which one is on top of the other, which one's coming through at the right time, which ones are actually not even mentioned. That's been my little challenge setting up these PowerPoints. So if you see everything going wacky, that's just because when I put these PowerPoints together, it's very hard to see when and where each and every animation is going to go. But for the record, that was just to be clear. Our mole ratio is 1 calcium chloride to 1 chlorine to 1 calcium metal to 1 chlorine gas to 1 calcium chloride formula unit. That is the ratio. And with this, 0.466 moles of chlorine will yield 0.446 moles of calcium chloride. You can see the Cl2, Cl2. But just remember, this is no longer chlorine gas. This is 2 chloride ions in a 1-to-2 ratio with calcium ions. I take those moles of calcium chloride product, I multiply it by the gram molar mass of calcium chloride over 1 mole, so my moles cancel out. I get 49.5 grams of calcium chloride. What I was told in the problem itself is that 10.6 grams of product are made. The percent yield will therefore be my actual yield divided by my theoretical yield, which I did through my stoichiometric calculations, times 100% means I get 21.4% yield in this reaction. Not a great yield, to be honest. Most people in most processes would be trying for a much higher yield than that. This is another problem. I think it is a very excellent problem because it does challenge you to make multiple mole conversions. 4.00 times 10 to the 24th molecules of nitrogen. So we need to remember nitrogen is N2. Hofbrinkel, nitrogen is one of them. 4.00, we're talking about numbers here. So I'm going to do my 1 mole per 6.0 times 2 times 10 to the 23rd particles in this case. It's reacted in a flask containing 55.0 liters of hydrogen gas at STP in a synthesis reaction, and only 14.5 grams of product are produced. What is the percent yield? Well, the first thing you would need to know is what product would you make. The most common product you could make with nitrogen and hydrogen coming together is ammonia. I hope you can recognize that. It is already balanced. I didn't go through the trouble of making it, writing out, and then having you balance it later. This is an extremely important reaction. This is the one that allows us to take atmospheric nitrogen, hydrogen from water, and produce ammonia, which is a building block for many fertilizers. Really, the world can't sustain the populations it does without an ability to make fertilizer. Bacteria do a great job of it, and if we were very smart about how we produce our food, maybe we wouldn't need to necessarily rely on this process. We may not need to rely so heavily on chemical fertilizers, but at the moment, as the world stands, and we do need to grow food for everybody every year, this is the only way we're able to sustain so many people. This is another reason, with the addition of better healthcare, better vaccines, fewer diseases. This is one of the other main reasons why our population has exploded from 1 billion in the 1800s to almost 8 billion now, and by the time we get to 2050, it'll probably be 10 billion. And finding new ways of growing more food for more people is going to be an enormous challenge that the world needs to face. That's why, if anyone's interested in careers, agricultural science, plant science, they are really looking at a expansive career, because there is such potential for, or such need for, growing more food on the same planet, because the planet isn't getting any bigger, and we're still going to need to grow food for everyone. Step 2, as we've always done, is to take our units and convert them into moles. And I see that I have a misprint here. What I did was I borrowed some of these things I just redid some of the slides, which means that some of my units I accidentally left. Okay. So I have 4.00 times 10 to the 24th molecules of nitrogen. And then I would multiply that. My conversion would be 1 mole over 6.02 times 10 to the 23rd particles. In this case, they would be molecules of nitrogen. That gives me 4 divided by 6, gives me 0.664 times 10 to the first, because I subtract my exponents, which would be the same thing as saying 6.64 moles of nitrogen gas. For hydrogen, 55.0 liters of hydrogen times 1 mole over 22.4 liters. Again, pay attention to your units. I need to pay attention to my units a little bit more also. That gives me 2.46 moles of hydrogen gas. Already we can see which one of these is going to run out first, because it's 1 mole of nitrogen to 3 moles of hydrogen. Here we have almost the opposite. We have almost 3 moles of nitrogen for every 1 mole of hydrogen. So the hydrogen is definitely going to run out first, which I can show you right here. Because of that conversion, again, it's a 1 to 3 to 2 ratio. If I used up all of my hydrogen, I'm not using even 1 mole of nitrogen gas for that. If I used all of my nitrogen, I would need 3 times this amount in order to make my ammonia. I don't have 18 moles of hydrogen. I only have 2.46 moles of hydrogen. So now for my conversion, I do my 2.46 moles of hydrogen. My mole ratio is 2 moles of ammonia for 3 moles of hydrogen, because it's asking about product. That's my only product. Once I do this, I do 2.46 times 2 divided by 3, I get 1.64. My moles of hydrogen, these units cancel out. I end up with 1.64 moles of ammonia. Now, what's it asking for? It's asking for grams. I'm going to have to calculate a percent yield. So I do 1.64 moles of ammonia times 17 grams, the gram molar mass of ammonia, 14 for nitrogen, and then 3 hydrogens, 111 is 17. Over 1 mole of ammonia, I get 27.9 grams of ammonia as my theoretical yield. So the percent yield would be the 14.5 grams divided by 27.9 grams, my actual yield as it's stated in the problem, divided by my theoretical yield that I just calculated from stoichiometry, times 100, I get 52.0% yield, which isn't terrible, but it's not great. Why this reaction is so important is because very few things in nature are able to use atmospheric nitrogen as a source for building blocks of proteins and nucleic acids primarily. So this process allows us to do that much more efficiently, making an accessible accessible nutrient source for plants. Some bacteria can also do this. Nitrifying bacteria can do this, but it's just a matter of getting those plants to grow. I mean, if we could do this in different crop management strategies, we could do this in genetic engineering. We can insert the genes that bacteria use to produce ammonia. We could insert them into corn or another plant. But at the moment, we're going to be dependent on chemical fertilizers like ammonia to feed so many people. Could we get better over time? I sure hope so, because there are a lot of issues with nitrates floating or nitrogen compounds floating into waterways and causing contamination, those sorts of things. So big career for those who are interested in some sort of way of modifying this process or improving this process so we can still continue to feed more and more people on the same amount of land. With that, hopefully you'll consider what we can do to make the world a better place. And in the meantime, that is how we do percent yield and limiting reactant.